way of thinking about the criterion. Okay, so what we're going to do now is we're going to take this relatively busy slide and we're going to unpack it. Just to set you up, we're going to put this into 3 different panels in the next slide. And we're going to take this and put it right on top, and then I'm going to pull off the left section and put it in the middle, and I'm going to pull off the right section and put it on the bottom. Okay, so you can see how this all hangs together. Here we are with this busy slide, still probability always on this axis, level of neural activity. Here's our criterion, so hopefully this top panel looks very familiar to you. We saw it in the last slide. Okay? Yes, I see it, no I don't. I'm going to now unpack this one on the left. I'm going to put it here. I'm going to unpack this on the right, and I'll pull it all the way down here. And hopefully you can see some correspondence between what's going on in these two and something that we had seen earlier called the stimulus response matrix. Remember that we have correct rejections and false alarms when the stimulus is absent. That's a catch trial, and that's going on right here. Correct rejections, false alarms. We have only the presence of noise distribution, a catch trial that has only background noise, no stimulus to be detected. Okay? If we now look at the bottom row of the stimulus response matrix, the stimulus is present, and we report either no, that would be a miss, or yes, that would be a hit. We see that also here on this slide, misses and hits. Okay? So here we have a cartoon of what's going on in the underlying neuroscience, the underlying neural activity, and we're superimposing on that something that you and I have direct access to as experimental psychologists. We can say on any given trial, we know that the stimulus was present or that it was not, and we know what their response was, either yes or no, and we can classify any one of their responses then in this 4-part way. Right? As a correct rejection, a false alarm, a hit or a miss, that superimposes very nicely on this unpacked version of the criterion slide that we had a moment ago. Right? In this particular case, this participant has D prime, I'll call it 1, and they have a criterion such that we're about middle of the road here. This is said to be a neutral criterion. What I'm going to show you in the next slide is the same D prime level, and everything will remain the same, except the criterion will now shift. And it's going to shift in this direction. It's going to shift over to the left. Okay? So it used to be here. We now have a leftward shift. And what that means is that this person now needs lower levels of neural activity before they're willing to say, yes, I do detect that signal. So with just a little bit of nervous activity, a little bit of sensory activity, and sensory evidence, they'll say, yes, I did detect this. This would generate a relatively liberal response. A relatively strong inclination to say, yes, I detect the stimulus. Okay? So when we have a leftward shift, we say that this is associated with a liberal response bias. We don't need very much neural activity or sensory evidence to conclude, yes, I see it. The flip side of that is we can have the criterion shift instead to the right rather than to the left. So it's to the right of the neutral point, and we still have everything else remaining the same, but here's a cartoon of somebody more like Connie, who requires higher levels of sensory evidence before concluding, yes, I see it. Okay? So now what we're going to do is see if we can understand some numbers associated with these biases, a relatively neutral bias, a liberal bias, and a conservative bias. So just as D prime is the statistic for sensitivity, beta is the statistic that we will use to reflect the criterion. Okay? So when beta is equal to 1, the criterion is said to be neutral. Okay? This person is about as likely to say yes as no. Okay? That person is relatively neutral. When we have lower levels of beta, this is now the equivalent of a leftward shift on the diagrams that we had seen before. The criterion is said to be low. This person has a liberal response bias, and when there's a moment of ambiguity, they're inclined to say, yes, I saw that stimulus, or I heard that stimulus. By contrast, if we have a beta value greater than 1, so 1 is our neutral point. If we're less than 1, it's liberal. If we're greater than 1, it's conservative. The criterion is relatively high here. This is a person who requires a lot of sensory evidence. Let's see if we can understand where these numbers come from. They come from a level of, I'm going to dial back just a little bit, they come from a level of comparison between the probability associated with that distribution and that distribution. In this class, we're not going to get into how you compute beta. If you take one of my upper level classes, or maybe the lab class associated with this, we will actually begin computing some of these ratios. But for right now, all we really need you to know is that beta is centered on 1, Lower levels correspond to liberal response biases, the inclination to say, yes, I see it. Beta values greater than 1 correspond to the inclination to say, no, I don't see it. Okay. All right, so that's our background for signal detection theory in words and in pictures. Okay. Now what we're going to do is see if we can apply some of these ideas to a broad variety of settings. Okay. So signal detection theory can be used in perceptual discrimination experiments. I've already given you an example of Coke and Pepsi. Okay. Let's see if we can use another example. Let's say that we were interested in looking at some moving stimuli, and we want to measure, for example, how sensitive you are to measuring speed differences or detecting speed differences. Sometimes stimuli are moving very quickly, sometimes they're moving very slowly. So we need to figure out how sensitive you are to detecting the speed at which stimuli move. This is important when we're estimating whether it's safe to cross the street, how fast is that car coming our way. Maybe you're a baseball player or a cricket player and you're about to hit the ball. You need to estimate how fast that ball is coming toward you. Lots of ways that we need to estimate the speed of a stimulus. Okay? So what we might do is set up a standard stimulus that moves at a certain speed, and some of the stimuli that we put your way are going to be faster than that standard speed. Others are going to be slower, that standard speed. And your task on any given trial is to report whether this given stimulus is faster or slower than average. So instead of saying yes or no, you make yes, the second stimulus was faster than the first. That might be one of your responses. Or no, the second stimulus was not faster, it was actually slower. Okay? So you can imagine that this criterion can shift leftward or rightward, just like it did. And if it shifts leftward, okay, then we need lower levels of neural activity. In this case, we might call this the neural activity that corresponds to perceived speed. Maybe we only need a little bit of sensory evidence to suggest that, yes, that second stimulus was faster. Other folks, in a moment of ambiguity, might have this shifted over to the right, and they would need a lot more evidence to conclude that a particular stimulus was faster than another one. Okay, so this is an example of a discrimination experiment, something akin to the Coke and Pepsi experiment that we had before. Okay, signal detection theory can be used in non-perceptual experiments. So we'll move a little bit beyond sensation and perception, and we'll see if we can get this now applied to something that you might remember from Intro to Psych when you learned about memory. So we'll think about this cognition experiment, where it might be the case that the professor reads you a list of words on day 1. Okay? Then on day 2, the professor brings you back and reads you another list of words, half of which were on the original list, and the other half are brand new words. And your job is to report that this word is one that you recognize from yesterday's list, or one that is not recognizable to you. Okay? So it's a yes-no kind of experiment, and now basically we're asking you to, if you will, detect the presence of a previously presented stimulus. So you can think of this then as a type of detection experiment, as we had done before, but now what we're detecting is a memory. Right? Did I see this stimulus once before or not? So still probability over here. You can think of this as a neural activity axis as always, but now the nervous activity is not going to be nervous activity relating to sensations, but rather to nervous activity that relates to something like memories. And up here I have a strong nervous activity associated with, or neural activity associated with a memory. Sometimes I'm not getting any neural activity associated with a particular memory or a particular stimulus. So here's my criterion. Okay? And if I have a high level of memory strength or nervous activity that pertains to that old stimulus, I might say, yes, I recall that. And over here I might say, no, I don't recall that. So it's just like Libby and Connie again. Maybe there are some very obvious cases that both young women remember from the previous day. Other cases where they're absolutely sure that they didn't see it the previous day. But there are cases where it might be ambiguous. And here again, it might be the case that Libby and Connie differ from each other with respect to the criterion. Libby might say that she has a lower criterion, and that she recalls a lot of these items. She will have a lot of false alarms, unfortunately, but she'll also have a lot of hits. Okay? We could say of Connie that if we get a motion this way, we would have many fewer false alarms and many fewer hits. But the good news is that she's going to be missing less often and correctly rejecting more often. So basically the liberals on the left and the conservatives on the right, and that's easy to remember, are going to have these complementary sets of error patterns. Okay? Neither one is better or worse, they're just different, and we can quantify all that using d prime and beta, in signal detection theory. So this could be subjective memory strength. A couple of other ideas that you might think about. You might think about our own legal system. You might think about the idea that we might have a stimulus, that is to say that we have a person in front of us, a defendant, who's either guilty or not guilty, and you have the jury's decision, okay, the jury's response, guilty or not guilty. Well, we can make type 1 errors and type 2 errors, we can correctly reject, we can hit, and so forth. All of that can be laid out the same way. Whenever we have a binary response, yes versus no, guilty versus not guilty, we're going to have some dividing line, yes on this side, no on that side. Okay? And it might be the case that we have a very strong level of evidence for the person's guilt, or maybe relatively no evidence for the person's guilt. And we can see that we can impose this kind of thinking, where we can get a D prime, and we can get a beta out of any system that's offering a binary response, guilty or not guilty. We can talk about this with respect to computer systems. Your own computer has an email system that might have a spam detector. Okay? The spam detector either allows email into your mailbox or not. That's a yes or no decision. And you can make your tolerance on your email system relatively liberal by moving it down this way, or relatively conservative by moving it that way. Okay, so here's our learning check. You might want to be able to do the following. First, draw two bell-shaped curves. We call these Gaussian curves, okay, after Gauss, the mathematician, who discovered this regularly recurring form of naturally occurring phenomena. So we're going to draw these two bell-shaped curves with the same mean, but different standard deviations. So they might be right on top of each other. That would mean that they've got the same mean, but one of them is relatively fat, and one of them is quite narrow. Okay? So the narrow one has a small standard deviation, the wider one has a big standard deviation, but they're lining up right on top of each other. Here's the narrow one, here's the fat one. Okay? Draw two bell-shaped curves that have the same standard deviation, but they have different means. That might be something like this. They're equally fat, but one is positioned higher and one is positioned lower on the x-axis. The relative position on the x-axis would correspond to their means. Okay? Draw one signal detection theory plot for a subject who has poor discrimination, and another signal detection theory plot for a different subject who has good discrimination. So again, this is poor discrimination. The two are right on top of each other. This is better discrimination. Finally, on the signal detection plots that you've just completed, draw a liberal criterion for one subject and a conservative criterion for the other, and make sure that you label them each clearly. So in this case, we draw that vertical line relatively leftward-ish, okay, a little bit closer to the left side of that axis. If this person has a liberal response bias, they don't need very much evidence to conclude, for example, that the stimulus was present, or that these are different stimuli, or that the defendant is guilty. Okay? If on the other hand we have on the right-hand side the position of our criterion, then we might say at that point we have a relatively conservative responder, and that person demands very high levels of evidence before reaching the particular conclusion that we're measuring, which might be a different response, or it might be a yes, I see it response. Okay, so that ends our presentation of signal detection theory. Please feel free to roll back through those slides and identify any questions that you might have for class. See you in class.